the chief scientist of Quantoven, and he was a professor in Oxford. He's now emeritus fellow at the Wilson College and a distinguished leading researcher at the Privilege Institute, who will talk about from quantum in pictures to practical NLP, music, and understandable AI. I'm sure you're all familiar with Bob's work. Don't want to take any more of his time. We just say, please, when you have questions, take this so that people in YouTube can hear you as well. Bob, whenever you're ready.
Okay, thanks Myers. Thanks everybody for having me here. I've been coming here for some 15 years now, at least. At some point I wasn't welcome anymore because I was too much of a bad influence on the work capabilities of some of the students of Philip and Shazlavan. But I'm allowed in again, seems. Okay, so yeah, I've got a pretty non-standard change of career recently. So for a long time I was a professor at the University of Oxford. Then I built a big group there, and lots of people actually, there was always a lot of connection with Vienna, and people sometimes mutually visited and all that. That group still exists, and now two of my former PhD students, Stefano Goggioso and Alex Kissinger, and also Jonathan Barrett, they're running the place now. Although I'm still like, you know, like master of the puppets. Okay, I left Oxford, handed it over, and I became chief scientist at what was then called Cambridge Quantum. Cambridge Quantum didn't last very long, as you can see. And then I became chief scientist in what is called Quantinuum. So Quantinuum was the result of a merger of Cambridge Quantum and part of Honeywell. So Honeywell maybe makes these things there, the control systems for your whatever and whatever. So they actually had been building quantum computers, so we went together and we formed this thing, Quantinuum, and that's now the biggest quantum computing company in the world. We are some 500 people now, so it's a big thing. Right, but besides that, I'm also got my own team in Oxford. I had my own team in Oxford, so that's how they look like. And I know I'm now going to envy a lot of people. I didn't write a single grant, of course. I just hired them, which is a good thing, given how many grants I wrote before. Anyway, so this is our logo. We got T-shirts of them. I'm not wearing this T-shirt. I'm wearing another T-shirt. I'll explain about this T-shirt. So we're in the T-shirt business now. This is our basement, paid for by the company. So that's also a bit different than academia. Okay, language of quantum. So John von Neumann. John von Neumann, of course, is the father of the quantum mechanical formalism, going back 1935. And one of the most important things for me about John von Neumann is that it's one person who was able, 3 years after the publication of his book, The Mathematics of Quantum Mechanics, Mathematics Formalism of Quantum Mechanics, which we still use now, to basically denounce it 3 years later and say, I don't believe in Hilbert space no more. Now, what is important here, what important is that somebody is brave enough to do that, for one, that he basically spent a lot of the remainder of his career to come up with an alternative and failed, but in the process invented 3 or 4 new fields of mathematics. So he wasn't waste at all. No question? No? Oh, okay. But an important thing for this talk is that von Neumann felt, and this is from the first time he started writing about things on how to build an alternative quantum formalism, he felt that measurement was at the core of quantum mechanics. And even in his book, he already had some sort of informal proof of that there is no hidden variables and all that. So this was all very early. Von Neumann kind of started foundations of quantum mechanics in that way, with like, and he sort of almost posed the measurement problem. And of course now everybody, when they talk about philosophy of quantum mechanics, they talk about measurement problem. So this is a consequence of Neumann, like the thinking that the measurement is probably the most important thing about quantum mechanics, and whatever effort he tried to come up with new quantum formalism, it was always focused on what is quantum measurement, how can we understand quantum measurement in the best possible way, conceptualize it, and then build a formalism around it. That was sort of Neumann's view. This was Schrödinger. So the thing I showed from before was from 1935. And people know this article probably of 1935. That's where people sort of start talking about entanglement and stuff like that. But the important sentence is here. So he's talking about composition of systems. I would not call that one, but rather the characteristic trait of quantum mechanics. So for von Neumann, it wasn't measurement. Unlike what everybody now thinks, that quantum measurement is at the core of understanding quantum mechanics. For von Neumann, it was composition of systems, the tensor product. That's at the core of understanding quantum mechanics. Nobody followed von Neumann in that. This was a paper which was not, or that opinion was never followed up, like, because everybody was, huh? Yeah. I mean, huh? Oh, so, yeah, Schrödinger, sorry, Schrödinger. You know, everybody was following von Neumann. Everybody was just following von Neumann in the statement of what the problem of quantum foundations actually is. Right, so in 2004, Samson Abramsky, a computer scientist, and actually not a computer scientist, a philosopher. And he was actually in the same class as Jeremy Butterfield, and they had a philosophy reading group together, Jeremy and Samson. Then Samson became a computer science professor, one of the biggest in the world. And he's the one who hired me when around 2000, 2001, when you were doing quantum foundations. There was just no future. Maybe they were outside of Vienna, possibly outside of Vienna. There was no future for anybody. He hired me in a computer science department. And then we wrote this paper, Categorical Semantics of Quantum Protocol. And that was really a realization of Schrödinger's view that you build a quantum formalism which starts from the idea of how you compose systems, and then you try to understand and conceptualize the composition of systems without bothering about measurement initially. That was really sort of the thing we did in this paper, and then we were able to show some things like quantum teleportation and some other stuff early on. But we used pretty heavy mathematics. We used some pretty heavy category theory, because that was sort of the natural mathematical structure to do that. Okay, so all the category theory was around, and people call it Australian category theory for some reason, because a lot of it was developed in Australia. So we just picked up the Australian category theory. We added a dagger, and we had to add one piece of structure just to account for complex numbers. Really, that's what it is. And we call it a dagger. Okay, this is Roger Penrose, Oxford. Who got his Nobel Prize for black holes. But another thing Roger did was starting to draw pictures like that when he was still an undergraduate student. Because he had to learn relativity and lots of stuff about relativity theory. He hated the notation, and he came up with his own notation as an undergraduate student. This is from a paper, I think, 1970, when for the first time this actually appeared in the literature. But he was doing this much earlier than that. Now why do I bring this up? I'm trying to bring this up in contrast with, on the one hand, this very heavy field of mathematics, which is monoidal category theory, which I started from, and then these simple-looking pictures. Because there actually were two category theoreticians, André Joël, who's a famous mathematician by all means, and Rostrit, who actually had shown that on the one hand, the monoidal categories, which we relied on, and we formulated quantum mechanics in, and Penrose's pictures were actually the same thing. So there was a way to basically create some kind of isomorphism. It's not trivial how you do that, it's very subtle, but to basically show that whatever you can do with all these axioms of category theory, you can kind of do with the pictures as well. It's the same thing. Okay, so then a year later, I wrote this paper, Kindergarten Quantum Mechanics. Historically, I was actually drawing pictures before the category theory paper with Samson. I had a paper in 2003 which was called The Logic of Entanglement, which was all about pictures and deriving teleportation. But at that time, people didn't trust that it was actually mathematics. And I didn't know about like all these connections between category theory and these pictures, but it turned out that like what I was doing was actually perfectly good thing to do, although it didn't enter the paper. But then 1 year later, I wrote this paper, Kindergarten Quantum Mechanics, so I redid everything again. Same paper as the one with Samson, but now just with pictures, the stuff we did. So we start to build up the start of new quantum formalism just with wires and cups and caps and stuff like that. Okay, he was a little bit of quantum mechanics. You could derive some stuff, but it was by no means all of quantum mechanics. By no means all of quantum mechanics, and people were already quite cynical that this would lead ever to anything. So the people say, this is never going to lead to everything. Say, maybe we can do all of quantum mechanics with pictures. Nah, no chance, no chance. So people were quite cynical about it. Now, the sort of mathematics you use is stuff like this. Like, I mean, a lot of people, I've seen this, of course, many times. It's about like you take a wire, you bend it, and then you yank it, and this is the same, because a wire is a wire. That's the sort of thing. And then you get some non-trivial stuff out of it easily, because, for example, if you take a box like that, and you wire the output to the input, and the input to the output, and you yank it, that's the same as taking a transpose in linear algebra, it turns out. So suddenly all of linear algebra became sort of an instance of all that stuff. So it was kind of cool. It was kind of cool. But again, like it wasn't really producing anything new. It wasn't really producing it. I mean, as far as I'm concerned, it was entirely new, the whole thing. But in the mind of the mainstream physicist, this is not new. New language doesn't mean anything new. That's sort of the, it's a weird thing. Anyway, 30 years later, Picturing Quantum Processes. This is like this big book, which I wrote with Alex Kissinger. And this was the course of quantum computing we were teaching in Oxford at the computer science department. So this is a full-blown course on quantum computing, everything in diagrams, algorithms are in there, everything what you want in a quantum computing course, everything, non-locality is there, of course, GHZ version, which is much more elegant in this sort of language. Everything's in there. Quantum computing, circuit optimization, you're a specialist now in compilation using diagrams. So everything was in there, and as well as like how does Hilbert space relate to all this stuff? Because we derive Hilbert space from the diagram, so that people, if they leave that course, they can actually do the boring old normal language too, the Hilbert space language too. And okay, I'm showing off this T-shirt here, and I'm not trying to make money here because I don't get a penny on it. It's since I'm in a business, Alex wanted to go in business too, and so he went in T-shirt business. Everybody goes in quantum computing, even in T-shirt business. So you can, but this is Dave the Dodo. Dave the Dodo, you can buy it online in Etsy. 5 years later.
Is David Dodo a version of David Deutsch?
Oh, nothing to do with David Deutsch. Nothing to do with David Deutsch. I don't know why he called him Dave. That was Alex called him Dave. I don't know why. I honestly don't know why you would call that thing Dave. Okay. Oh no, problem. Is this from Space Odyssey? Is that a Dave? What is the name of the computer? Dale. Oh, okay, no, it's not that. Okay, I don't know where he came from, Dave. Okay, 5 years later. Okay, okay. Where is Dave?
But Dave was the guy who was dismantling HAL.
Yes. I knew there was a Dave there. There was a Dave there. Okay, 5 years later, this book, you've got it. So I sent 6 copies to COECKE months ago. It seems that so far 1 arrived. This is the UK mail system to blame, and Brexit. Anyway, so why, if you write a 1000-page book like that, which is doing well, would you write another book which is a bit thinner? And probably in the same way. So the difference between this one and the previous one is this one pretty much everybody can read. You don't need to know any maths. He doesn't have any math prerequisites. So, I mean, we already got positive reviews from kids as young as 10 years. And there is sophisticated stuff in there. There's sophisticated stuff. Non-locality proof is in there, for example, like non-locality, no broadcasting theorem is in there. So stuff you don't even find in mainstream books. This measurement-based quantum computing is in there. So stuff you don't find in mainstream books, in a book for kids. So that's what this is. There's a few more. You can buy them now on Amazon. I'm not advertising here because we're pretty much selling at loss because we don't want to make money out of it. It's actually the company who published it. But yeah, okay. So that's this book which is out now with Stefano Goggioso, former PhD student of me now, also in Oxford faculty, in the same group. And because kids don't read books anymore, we also videoed the whole thing, like with lectures and stuff like that. So they will come out. They will come out in a few weeks on YouTube. The delay is that some of the people lecturing are actually employed by university, and universities are places who cannot be trusted. I know I've learned this the hard way. Universities are places that cannot be trusted. So we want to protect ourselves, and And yeah, it's complicated. But anyway, soon. So like this is a moon, by the way. This is a moon. Moon balloon.
Dark side.
Yeah, it has a dark side. Because, I mean, you see numbers, and that's actually the only numbers we use in the book, angles, because initially we were going to use phases of the moon. You can actually, instead of using angles, just use phases of the moon. It's the same structure. But then Stefano started to draw all these pictures and he got bored. And at some point we say, okay, this phase corresponds to that number. This phase corresponds to that number. Right. I'm going to briefly take you through what's in that book. So I mean, a lot of people know this story here because they've been completely bored by me for 15 years or something. So systems and stuff like that, systems of, I mean, we call them particles in the book. Particles, they live in wires. A wire is a place where a particle lives. This can be an electrical wire, this can be a water hose, this can be the air where light propagates, anything like that. Well, that's a wire. So it can be an abstract wire, it can be a concrete wire. And then a box is something that acts on things that live in wires. Be it water, be it electricity, be it whatever, be it food. This could be a food wire. I mean, if you think of flowcharts, in flowcharts anything can go. It's like here too. By convention we read from bottom to top. Just a convention, no particular meaning. This comes from the physics tradition, from light cones are drawn from bottom to top, nothing more. Then you can plug them together, you can plug these together, and that's something we call a diagram, but you can call it whatever you want, it doesn't need a name. And things get, yeah?
So, just to make sure I'm clear, should I think of a system when it's, is it too literal to think of a system as being in the wire?
No, that's okay.
And that's it. That's like free evolution. That's
I mean, that's okay, like, because you can think of both a wave and a particle in a wire. So,
and so I should think until the system hits the box, so to speak, this is free evolution.
yeah. Yeah. It's an identity. And as we know in physics, the most difficult thing to do is an identity, because otherwise we would already have quantum computers. Light is pretty okay. If light is the opposite almost. Light doesn't like the boxes. Okay, so things get really interesting when actually you start to build new boxes from stuff you already have, like a wire. Like for example, here we take like a little cup-shaped wire. It has two outputs, and you have to think of this as like a state of two systems. Like a thing with only outputs is like a state. A thing with only inputs is like an effect, like a test. So here we see a thing with two outputs, which you have to think of like a two-state physical system. And this actually is supposed to be the Bell state. This is supposed to be the Bell state. And this is the corresponding Bell effect. And if you see this configuration, for those who never saw this talk before, what do you immediately see here? Yeah, I heard it. Somebody mumbled it. Yeah. This is the maths behind teleportation. So you got a Bell state, you got a Bell test, this post-selected teleportation. And you get it like that easy from such a wire picture. And then, for example, you can then take things like a box, you slide it along the wire, like here. And this is basically then generating, so whatever is here, this would be the transpose. This would be the transpose. So that shows like this idea I was saying earlier, that turning a box around is like generating the transpose. And then, of course, here we got it, post-selected teleportation. And then by making some sort of variable box here, you can build your Bell measurement, and then you do the corresponding correction on the other side. And okay, this is full teleportation. I mean, it's not as beautiful as what I've got here on my t-shirt. So this is full-blown teleportation in the X calculus, and you don't have this horrible squishy line there. It's full-blown teleportation with all the corrections just in a picture here. That's what you see here. But you need a bit more structure than that to do that. You need a bit more structure. So when we were there, so the question I asked at the time is like, what is this classical wire? What is this telephone wire? How does the telephone wire relate to the quantum wire? And that's something which I'm not going to go into, but you can read in the children book. It's basically a quantum wire is like a double wire, and a classical wire is like a single wire, and then everything works out perfectly. That's how simple it is. It's kind of what von Neumann already knew, because what von Neumann did is he took like a cat and a bra, and he said, okay, this is a mixed state. Now, suddenly, I mean, we would do a ket and a conjugate ket, which is exactly the same, by the way. And so then you get like actually two things, which is quantum, and then when you decohere, the probabilities that come out is classical. That's how it works. That's how it works. It's as simple as that. Right? Now, to go to full-blown quantum formalism like here, that you can do everything in teleportation, just like with wires and things, you need something more than wires. And what is more than wires is spiders. Okay. So what is a wire? A wire is a thing that connects two endpoints, right? And then you can connect these endpoints together and stuff like that. A wire is really a thing which connects two endpoints. The behavior of a wire, so the actions which govern wires, is that if you connect two wires together in one place, you get another wire. You gain nothing. You just get another wire. You gain nothing. So a wire together with wire is wire. You gain nothing. It's a bit boring. So this is a spider. This is a spider, and the advantage of a spider is it has more than two endpoints, or less if you want to. I mean, it's brutal. It's not ethical, but I mean, it can have no wires. I mean, there kids do these things, you know. They pull out the legs. Anyway, so here is a spider, and the rules which govern a spider are exactly the same as the rules which govern a wire. If you plug two spiders together, you get another spider. However, it's not necessarily the same spider as the one you started with, because you have to do here we got a 1, 2, 3, 5 legs. Here we got 4 legs. There we got 7 legs. Well, it's a different one. It's a different one. And things become interesting when you actually introduce two kinds of spiders. Okay, let me say, because I mean, you're not kids here. So there is a theorem, you can prove a non-trivial theorem, that this axiom alone, when you interpret the spiders in Hilbert space, you interpret these wires as Hilbert spaces, the spiders as linear maps in Hilbert space. So you got a Hilbert space, you tensor them together. Hilbert space, you tensor them together. And so this is a linear map between these things. If you interpret the spiders like this as linear maps between Hilbert spaces, where the wires are just tensored together Hilbert spaces, then these axioms alone tell you that the spiders are in one-to-one correspondence with orthonormal bases in Hilbert space. So this is an axiomatization of orthonormal bases. I mean, it looks nothing like an orthonormal base, but it's an axiomatization of orthonormal bases. And what is beautiful about this is there is no sums around. There's nothing like sums around. There is nothing like, how do you call that, scalar multiples around. Yeah?
How can we see the orthogonality?
Oh, wait. So basically, so the thing is, you got an I'll tell you, you got an axiomatization of orthonormal bases in terms of a language which only uses the symbol of tensor product. There's no other symbol you use in expressing this thing, just processes and tensor product. So this is kind of what von Neumann was hinting at. Schrödinger. That tensor is maybe more fundamental because you can derive other stuff from the tensor. And here we're deriving the notion of orthonormal basis from the tensor structure without needing anything. Now, to answer Marius's question, so basically the orthonormality is in the is that one way to define these spiders is basically taking an orthonormal basis and then summing like this, like this over the basis vector. So I've got a basis, these are just my whatever it is. So I build kets, I build bras, some are the inputs, some are the outputs. So that's where you see the number of legs arising. And if you define a spider like that, then this equation is valid. The theorem says that anything that obeys this equation is of this form for some choice of a basis.
This is contraction.
Huh? Yeah, it's just a little product here. So it's just going to map up whatever is the same. And like one example here is like, for example, this 2 out, 1 in. What is this? 2 2 out, 1 in. It's a copy, coherent copy. So a coherent copy, and by the no-cloning theorem, we know that such a thing only copies the basis vectors. So this spider, if you take this spider, 1 input, 2 outputs, the things it copies will be an orthonormal basis by the no-cloning theorem. Now, to prove what I just said, that all the things solve these which satisfy these axioms are of this form, that's quite a bit harder. You have to go to lots of results of C-star algebra and stuff like that. It's pretty heavy. But yeah, so an orthonormal basis, and this thing is the same. Okay, now I can go to the next stage. Let's introduce 2 kinds of spiders. So now we know 2 kinds of spiders means 2 kinds of orthonormal bases. You got and what happens with, so okay, now what I'm axiomatizing is not anymore what is a spider, but what is the interaction between 2 particular kinds of spiders. And in this case, we want to capture unbiasedness. A Z and an X, for example. 2 kinds of spiders which are unbiased. And it turns out this equation is equivalent to a mutual unbiased basis. This is mutual unbiasedness of basis. What happens here? We see 2 spiders, and they connect with 2 legs. 2, that's important, 2. And then they fall off. And we'll see later. So the way you can think about it is like, there is information. So here you got a spider, and now you have to follow me. Forget about this leg, forget about this leg, forget about this leg, and forget about this leg. So I've got some classical thing here. I've got some bit maybe coming in. This is a copier, or no, it's a ket, a basis vector. This is a copier. I've got 2 basis vectors. So this is like a quantum state now. And this is, you have to think of this as a measurement. It takes a quantum thing in and a classical thing out. And basically what it's saying is, whatever comes in, there is no trace anymore that comes out, because the 2 bases are unbiased. And that's why we can just drop the wires. So that's the intuition behind this equation. Right? So this is actually expresses unbiasedness. The fact that if 2 spiders of different colors meet, they got 2 legs in the middle, they fall off. I mean, it's because of the quantum. Quantum is 2. Quantum is 2. So you have to think of this as if you just think of here being 1 leg and this one is not here, I'm encoding classical in the Z basis as quantum, and then I'm measuring the X basis. And then you know nothing goes through. Everything gets lost. And that's so it's the same as these wires not being there.
Should the connections be colored as well?
Yes. 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 Well, not the quantum, it doesn't matter, but classically the value will actually connect on the is connected. So if you measure in a color, then the variable will carry the data of what it is measured in. So the classical wire should be colored. 100% correct. So I'll write, I mean, there is no color here, but so well, it's not necessary, it's okay. It's okay, it's okay. I mean, in the book which we published with my company, Quantoven, has very beautiful colors. The book we published with Cambridge University Press is black and white because they said colors are too expensive. So that's the advantage of publishing with a company. So this really is how it looks. So you got something classical, you encode in 1 basis, you got something quantum, 2 wires, you measure in the other basis, and basically this is noise. This is noise. So all you get is noise. So that's kind of how it works. This is the expression of unbiasedness. I mean, I'm not going to go into it, but if you go into the X calculus, oh, what happened here? Okay. I have to pull it out and in, huh? Oh, it's back. So if you go to the X calculus, which I didn't want to go into detail in, then we got a more complicated expression between these 2. It turns out that, for example, in 2 dimensions, the Z and the X bases obey more equations than just this. This is like a stronger sort of axiomatic system that governs them, and that's what we use in the X calculus. But let me just get to this is completely stupid, simple computation. So basically, it turns out if you connect the green and the red spider like this, that is the same as a C0 gate. So this is the green is the control, and the redis were actually unigate or not. So here we got a little quantum circuit with 3 CNOT gates. Then you can ask yourself, okay, can we simplify this? Can we simplify this? So you see 3 spiders here, green, 2 red. Okay, so we fuse them. Right? You remember spiders fuse. We see 2 wires in between here, so we can drop them. And now we got a spider with 2 legs. Well, okay, that's just a wire. That's where we start from. And so we've simplified this simple circuit to this simple circuit. It's a completely trivial calculation, I agree, but you see kind of the principle of how the spiders actually allow you to do something that's highly non-trivial. And as it turns out, this method of simplifying quantum circuits is now the state of the art. There's nothing better. Sometimes you mix it with other methods, but this sort of underlying use of the spiders is really what's built in, for example, the Quantinuum ticket compiler. It's built in there. So actually, so yeah, it's an amazing way to do this like optimization stuff and all that. Yeah. Okay, I mean, I'm not going to go through there, but this is like this is the statement of G8Z non-locality. You got four scenarios, the 4 different measurement scenarios, which you find in G8Z non-locality. These are your measurements, and then the phases here, they sort of change your measurement between X and Y. And that's what these phases here are doing. So this is an X measurement. It changes between X and Y. And this thing turns out to be a parity test. This is a parity test. The red spider with single wires is the same as a parity test. So this is the entire protocol you do on the quantum side. This is everything just in one picture. And then what happens, I didn't show you, but the sort of more advanced equation which we have for how green and red interacts for Z and X, like this stronger form complementarity allows you to commute these things through. And then essentially, basically, all these things, all these red dots are going to add up. So 90, 90, 90, 90, 90, 90, they are going to add up, and you get 180. You get 180 as a total sum. So what you get is like a red dot with 180, which is actually the the minus state, which is the which is the one state, sorry. And this is the statement of an hidden variable model. You got your variables here, which determine all your outcomes of your possible measurements involved in the protocol. You have the Y and the X measurements. So each gives a value. It gives this to all the possible scenarios. It gets copied through. And then you do a parity test. And you see there's 2 wires between green and red always, so they fall away. So we end up just with the top dot, which is actually the 0 state. And that's non-locality. 0 is not equal to 1. So this is how you prove something more sophisticated with this stuff. So okay. So I mean, if you want, I actually wrote something after Anton got the Nobel Prize, like, and my company published this, like, about how, the story of somebody like me who did a PhD in quantum foundations in the 90s, which was a pretty horrible experience, and so I was unemployed and all of that, and now this all sort of is intertwined with the stuff which I'm talking about now. Because Časlav knows the story about, he was one of the people who actually, together with Lucian Hardy and myself, were sort of building up quantum foundations to some extent over the past 20 years. This is, so there's a kid of 10 years who wrote a really nice review. So here is an interesting story, and that's also the experience of some almost 20 years trying to tell these things to people. The people who are the worst with this, and I should have put up some really bad reviews too, I forgot about it, are theoretical physicists. They have a serious problem with that stuff, because all they want to do is translate this to what they already know, and the translation is non-trivial. It's highly non-trivial. And then, so I've got, there's a review on Amazon, like, this is incredibly complicated stuff. Really. Because they can't map it in what they know. And the fact that, and there is also some ego thing, we know everything, we know everything. So it's impossible that something as silly like that could actually replicate things which have been complicated for many years. Okay. So one experiment now to prove them all wrong. One experiment we're setting up to prove them all wrong. I've been talking about this a long time. And the interesting thing is, I tried to get funding for this, and it was very hard to get funding for this in academia. Now my company is paying it, and in IBM. So it's going to be an experiment by my company and IBM. And what we're doing is like, we're teaching, the videos which I mentioned are going to be used for that, for teaching. So we're teaching a bunch of teenagers basically quantum mechanics in this way. We're going to take somebody from an Oxford University course, a bunch of students from an Oxford University course which get the mainstream stuff in Hilbert space. We're going to give them the same exam. A bunch of questions, either formulated in diagrams or Hilbert space, and see what, of course, we've done pre-testing and we know the kids are going to win. We know that. We just know that for a fact. I mean, it's not a surprise. I mean, this is a really simple thingy. This is a simple, trivial calculation. Try to do this with matrices. Try. This one with matrices is not easy. It's not easy. Okay, so this was the original paper from 2007. Ross Duncan and I, we wrote this thing, and it's now called ZX calculus. And it was a hard sell for a very long time. There was like a core of people working on the field and developing this thing further and further. But it was a very hard sell to like the mainstream community, people who go to QIP and stuff like that. Those kind of people doing algorithm and complexity, they really didn't want to know about this. So people doing algorithms. Now, what happened recently, especially with photonic quantum computing now becoming like industry scale, and you need to do fault tolerance and all of these things, it's sort of becoming the language for people doing photonic quantum computing. I mean, you see, this is from PsiQuantum, this X calculus is immensely useful. This is academic language, you know, immensely useful. So here is an interesting background story. So I don't know what you know, Naomi is now Terry Rudolph's wife. They're married. So that's his new wife, Naomi Nickerson. Huge fan of the X calculus. So let me go back to this paper, this first paper, which was never published, 2007. This was written by Ross and I on a bus in Iran next to Terry Rudolph. So we were sitting there on a bus like for 2 weeks, and Ross and I, we were writing this paper. Terry was sitting there. Oh, what is this stuff, guys? What is this stuff, guys? What is this stuff, guys? And he never picked it up, although Rob Peckens and people like his friends picked it up. And now he's advertising it because the first one never. No, there was other papers. Actually, partly thanks to Chazov, by the way. We got one in a New Journal of Physics when Chazov was an editor there. It's true, huh? I mean, this paper is very highly cited now, so it's really, really highly cited, so it can be disclosed, I think, in these circumstances, because we had a really hard time to get it anywhere. And it's really highly cited now, of course. So in photonic quantum computing, this is really a very, very, I know, Philip wrote a paper on ZX calculus, compilation of ZX calculus. So it's a thing which is taken over, and we are actually working on a book now, not ZX calculus, but a slightly extended calculus, which we call ZXW, and the book is going to call Picturing Quantum Photonics. Should be out in a year or something like that. So this stuff is incredibly suited for like photonic quantum computing, where you have the layer of the circuits and all the error correction. And it's super complicated to do it in any other way. It's just super complicated. PsiQuantum knows it. The Quandella's doing it. They're also adopting diagrams. Everybody's doing it. I know Xanadu hasn't said anything, but they just hired like a hardcore ZX guy. So you know what they're doing. So then I mean, this is sort of beautiful when I was saying that the complexity people really didn't like it. They really didn't like it. So this graphical. So this is a paper co-authored by Peter Shor, and Peter Shor has been teaching ZX calculus at MIT. So that's nice way to tell to all these people who sort of were saying for 15 years that this would lead to nothing. Anyway, so these are the companies we know are using now ZX calculus or something like that. That's the one. So that's a lot of them. Okay, I'm going to skip this. Okay, so why is this stuff so powerful? Let me check time. Okay, that's good. Why is this stuff so powerful? Because there's a theorem which these people proved, which says that any equation you can derive in Hilbert space with linear maps and your usual Hilbert space mathematics, you can derive with this thing called ZX calculus. And we now have it extended in all dimensions all finite dimensions, I should say. And we have theorems like that for every dimension now. So all that stuff, you can do everything graphically, all equations and things like that.
You can do it for all von Neumann algebra types?
Well, probably. I mean, if von Jones would be still alive, I probably would write him an email. He probably would say yes. He's my cousin, my academic cousin, von Jones. But I can't answer this with confidence. This is Jim Lemmek. So Jim Lemmek is a linguist. Well, he's actually a very famous category theoretician, mathematician, but he's also somebody who wrote a paper in the 1956 called The Mathematics of Sentence Structure. Mathematics of Sentence Structure, which basically was the first really beautiful paper where it is explained what mathematical structure you should use to verify if a sentence is grammatically correctly formed. So it's a completely different subject now. Eh? So you put words together, when is it grammatically correctly formed? So he sort of started, and you know, people like Chomsky, they did a lot of stuff based on that. So but Jim Lemmek was sort of the guy who started all of that. And then now we're back to 2005. That's when I had this paper, Kindergarten Quantum Mechanics. I was very proud. I was talking about it in Montreal. I was sort of explaining quantum teleportation to the category theoreticians in these diagrams. I said, okay, I'll present to you quantum teleportation. And then Jim was in the room and said, hey, Bob, this is grammar. I said, no, Jim, this is quantum physics, quantum teleportation. No, Bob, this is grammar. And as it turns out, he had come up with some new theory of grammar, new formalization in 1999, and he used exactly the same mathematical structures as this to basically verify whether a sentence was grammatically correct. So the categorical structure which governs both quantum teleportation and that sort of stuff on the one hand, and grammar on the other hand, is exactly the same. It's exactly the same thing. So he was right, and then 3 years later, I mean, I didn't care. I mean, at that time, my interest was not linguistics. My interest was like coming up with a diagrammatic quantum formalism. But then 3 years later in Oxford, I had some colleagues that was like Marnusha Zadeh, and she actually knew about this Lambeq stuff. I didn't even know about it. She knew about this Lambeq stuff. She had been working with him on it, like showing that it works well for Persian, for example. She had been doing that. And I mean, I don't want to say too much about it, but it's really just pieces of algebra like this, but ultimately, this is if you got a noun and a transitive verb, which happens to be, you have to think of a transitive verb as like a composite particle, where you got an antiparticle of noun, an antiparticle of noun, and then a sentence particle all smashed together. And then this basically is asking to get a noun on the left and a noun on the right to cancel out to actually form the sentence type. Does that make sense? That's what he's want. And that's kind of how all that stuff works. And now think a little bit like in Feynman diagram line. So this is like annihilation. The noun type and the anti-noun type, they annihilate each other. Noun, anti-noun type annihilate each other. Sentence type goes through. So this is the proof that a noun, transitive verb, noun, forms a correct sentence. That's how it works. This is a very simple example, but it works for much more complicated stuff too. And the important thing is you see these cup wires here, you see, which we used to think of as Bell states and stuff. You see them here emerging in this sort of calculation. So there was somebody else at Oxford. This is Steve Clark. At the time he was faculty in Oxford, then he moved to Cambridge, and then became a senior scientist at DeepMind, and now he's our head of AI. So now he's back with us at Continuum. So, and he knew about vector representations of meaning. So vector representations of meaning is what all these big language models now use. They represent meanings by vectors with multiple variables and stuff like that. But that idea was at the time still an academic idea. There weren't big language models. There had been no deep learning revolution, nothing like that. It hadn't happened yet. We're talking 2007, 2006 now. But Steve knew about these vector models, and he was like, as an academic, trying to study them, see what we can do. And then one big question at the time was, how can we combine grammar and meaning? So these vectors are meaning. This algebra is grammar. How we can combine them? And for example, if we have a bunch of words we know the meaning of, and we have the correct grammatical structure, can we maybe assign a vector to the whole sentence? Is there some algorithm which combines the grammar and all these meanings to spit something out? Huh? I mean, when Steve asked me this question, I went back in memory. I didn't understand much about all this stuff, but I did remember this. Saying that these diagrams were grammar. And what flows in these diagrams are vectors, meanings. Vectors, quantum systems are vectors. So this could as well be linguistic vectors, meanings. And so is this formula maybe the right way to combine grammar and meaning? So it turned out to be the case. It was spot on the nose. So we wrote this paper, Mathematical Foundations for a Compositional Distributional Model of Meaning. This is 2010. I think we had the idea in 2008. And this is kind of how it works. Now, the diagrams are upside down, as opposed to how we were reading diagrams before. Why? Because, I mean, time cones, physicists say how time goes up. Language, like a book you read from top to bottom. That's just it. There's nothing more to it. So we got here the word Alice. Think of it as a quantum state. Alice, the meaning of the word Alice, a vector. The meaning of the word hates, a vector. The meaning of the word Bob. And what you're doing here is you're feeding, almost like teleporting, the meaning of the word Alice into the verb hates, the meaning of the word Bob into the verb hates. They interact, they get entangled in a hatred way, and spit it out. Yeah? Alice gets here. So what this thing is doing is it's entangling Alice and Bob in a hatredship relation. And then these two wires here, these thick wires, think of it again as two thin wires, an Alice wire and a Bob wire, who come out now entangled by hatred. Yeah? You were there?
So I just wanted to ask, so linguists were already doing these types of diagrams, or
What they were doing was more like logicians. They were assigning types to words, but there was no meaning. There was never any meaning involved. It was so there is old work by Montague, and there was truth theoretic semantics for meaning. This was trying to derive, like a little bit like Aristotelian stuff. If we know that this sentence is true and this sentence is true, can we then figure out that this sentence is true? But this was all about truth and false. This was not about sort of, well, what is meaning? You know, like now meaning is a vector in I don't know how high dimensional Hilbert space. That's what people use as a model. I mean, it's conceptually philosophers hate this, but because but it works. It clearly works for, no, it doesn't work all the way. It works for some things. And I think ChatGPT is highly overrated at the moment. But, highly, all that stuff is seriously highly overrated. But I mean, it's a new thing, and it does thing nobody expected. But it's overrated in many of the aspects. So, okay, like I was saying, so we got here the meanings now. We got the meanings on one layer, and we got the grammar down here. And we combine them, and we get something out. And what you can do now is, for example, take this sentence, Alice hates Bob, and this sentence, Alice does not like Bob. And then you can see how they compare. Are they closely related, yes or no? And that means just that the inner product is large. If they're closely related, you get a big value for the inner product. If they're far apart, you get a small value. And so now you can compare sentences in principle. Okay, I'm not going to go into that. We actually also use our spiders in that stuff. For example, to model a relative pronoun here. I'm not going to go into that. Anyway, so I remember at the time talking to Steve and Mernush and saying, don't mention quantum. Don't mention quantum. We are just trying to solve a linguistic problem here, and if anybody's going to throw the word quantum in the mix, they're going to think we're a whole bunch of crackpots. I was telling them, don't mention quantum. And then immediately all these articles came out, the quantum linguist, quantum linguistics, quantum mechanical words. Okay, and at the time, like, okay, whatever. Now we're quite a bit further, and there's of course this guy, that if you got something that maybe is not quantum mechanical substance per se, but is modeled by quantum mechanics, then you're going to have a hard time putting it on a classical machine. And we experienced that, of course. When we were doing, we did a lot of experiments with this model. They did really good. They did much better than other stuff, but they didn't scale. The tensors blew up. Of course, the tensors started to blow up if your sentences became too long and stuff like that. And so we were struggling. And yeah, okay, what these guys said, yeah, stick it on a quantum computer. That's what he basically said. And then Will Zeng was a PhD student of me, and then went to work for Rigetti, and he recently worked for Goldman Sachs. He was the head of quantum there. We basically said, okay, suppose we stick it on a quantum computer, do we get algorithmic advantage for standard natural language processing tasks? And the answer was yes. I mean, at that time, it was just simple Groover-like speedup. Nothing more, just Groover, like search type of speedup, but pretty much anything you want to do with that stuff, natural language processing, you got a Groover-style speedup, always, everything. I mean, then basically, this was very theoretical. This was still very theoretical. I mean, I didn't believe that quantum computers would be able to do this in any time soon, of course. And then Ilyas Khan, who was the CEO of Cambridge Quantum, said, hey, Bob, you have to try this stuff. Like, you can use all the quantum computers I've got available. And then in 2020, we actually did quantum natural language processing on quantum hardware. So we trained the machine, we taught the machine some stuff, and then we asked the machine some questions, and we got the right answers. So, I mean, this was small scale. This was very small scale, but the fact alone that this worked was remarkable, at least for me. I thought it was shocking that you could actually do this question answering with quantum hardware existing. We're talking 2020. Things were much worse than now, by the way. Even then, and we did it on quite a small machine, actually. Okay, so then we start to do things bigger. And what we did next was we actually built a whole software around this task of quantum natural language processing, which basically takes in sentences or text or whatever, and then turns it into the right format, so you can actually stick it on your favorite existing quantum computer. And there's a lot of other choices you can make in the middle and stuff like that. But this is actually a really nice sort of software package. Is the name here? No, the name is not here. Okay, good. Well, the name is here. So we called it lambeq, which is the name of the guy who basically said like, hey, this is grammar, but with a Q at the end. I mean, that's a silly thing you do. It's a silly thing you do. But so, okay, I mean, it's really a pity that he's not alive, because he would have loved the whole idea of having his name there. He has never used a computer in his entire life. He was still alive in 2012. He never touched a computer in his entire life. So he would have seen the joke of that. Okay, so I mean, this thing is kicking in. Like, I mean, this is a team from IBM who then again did some more quantum natural language processing tasks using. So COECKE is the name of our formalism. I didn't come up with the name. I just hate it, but it's something somebody said and then sticked. This for distributional, co for compositional, cat for category theory. Whatever. Distributional means that you work with vectors and not like with zeros and ones. Compositional is the fact that you use grammatical structure and these sort of little algebras. And this was interesting. So this was one team at IBM, and this was another team at IBM, and they were all doing that stuff, and they didn't know from each other that they were even doing it. So they were all using the same formalism. But if you want to read more of it, so these three guys, they actually wrote a really nice blog post, an introduction to quantum natural language processing, very easy to read. And they explain all the stuff we've been doing, what they've been adding to it. And they explain something more, which I think I'm going to now, this one. They also talk about this one, a quantum natural language processing approach to musical intelligence. So basically what we did is, so you got linguistic grammars, but there also exists something like musical grammars. You can write a grammar which generates music, just like, and says what is correct musical sentences and blah, blah, blah. So we substituted our linguistic grammar with a musical grammar, made it generate something, made it generative so that it starts spitting out stuff, because if you got a classifier, you can actually build a generator. And we called it Quanthoven. So I mean, this is all downloadable too, by the way. You can find this all somewhere on GitHub, so you can play around with this too. And then, so we spit out one song, I mean, which was called Bob's Cigar Buzz, and this became #1 in classical charts. Anyway, huh? It's rubbish. it's rubbish. It was never intended to be any good. It was just like, okay, like look, this is something we can generate. It was never intended to be good. But now we're actually doing it more serious. Now we're doing it more serious. And this, does anybody recognize this guy? That's Brian Eno. So Brian Eno now wants to hook up with us for this sort of quantum music stuff. I mean, he was the guy who sort of brought computers into music in the first place to a big extent. So I mean, I wasn't there because I was actually in Australia in this particular meeting. These are my collaborators, Konstantinos Mechanizidis. You know Konstantinos. Marios knows Konstantinos. Richie Young. Right. Okay, I'm out of time now. So.
Yeah.
Well, I mean, whatever I want. Well, let me just. So basically, this is what happens inside lambeq. Oh, just you got a sentence. Then we do some spidering inside. We do some spidering inside to actually, it's like what I said, to actually get these two wires out, like I said, like the Alice wire and the Bob wire. And this is like as if like H is now entangling Alice and Bob. And then we just start to deform it, using this calculus. We pull out the different colors, so now we get a CNOT gate. So this is the most interesting step, I think. You got this, and then you pull out this dot, and you get a CNOT gate. So it starts to look like a quantum circuit. Then you can, for example, compress it to make it 3 qubits instead of 4, and then you parameterize whatever's inside the boxes with parameterized quantum circuits. And that's basically what this stuff does. And then you use some classical optimizer, and that's what quantum natural language processing now is. And I'm going to skip all the rest.
Brief question, can you mention it? Where's the speed up? You said that the pragmatic speed up just in general.
Okay.
It's amazing it works here, but is there any benefit in terms of classical?
So I mentioned the previous paper with Will Zhang that we get sort of Groover-like speedups. And it's really the same as your closest vector algorithm type stuff. Yes. It's very much a search, like which is your vector closest to the one you want. Yes. If you want to, for example, classify something. I've got a text, and I want to know whether it's about sport or about politics, about romance. So you're actually looking for a closest vector. So that's typically the sort of speedups you get, and they're all Groover-like. Now we're doing much better. So what all I was talking about now is an old formalism from 2007, 2008, where we assign meanings to sentences, giving meanings to words. So for a couple of years now, I've got a new one, and this is being worked out a lot now, and this is about like a meaning of text. And basically, just think, I'm going to show you a circuit. Okay, just think of this, I mean, this wasn't made for it, but think of this wire as Alice, think of this wire as Bob, think of this wire as Charlie, think of this wire as Dave. And then a text is just stuff happening to these people, getting entangled, or changing or cutting their hair or stuff like that. So you get a big quantum circuit which gives you the meaning of a text, and it can be as deep as you want. So there's a new formulas we work with, and when you want to do this is pretty much the same as like simulating chemistry on a quantum computer. You simulate an evolution. So we expect similar, I mean, it's very hard to quantify this exactly, just like the chemists have the same problem, but we expect sort of the same speedups as the chemist for this one. So that's what we're hoping to do an experiment within a year on the Honeywell machine, because they're particularly good with deep circuits, and they are, I mean, I shouldn't call them Honeywell, I should call them Quantinuum. And I mean, I don't think I'm telling a secret if within a year they're actually expecting to get to the level that it's going to be pretty easy to get some supremacy going, stuff you can't simulate at all anymore classically. That's what they're expecting within a year. So we're going to stick this stuff on the Honeywell quantum computer within the year and see. So the idea is, for example, I mean, just to give you a metaphor, you got a detective story. All the information is there to figure out who's the murderer, but you have to be really clever to figure it all out together. Can we do this? That's the sort of thing I'm talking about, and that's super hard. That's just super hard if you would try to simulate this on a classical machine.
Okay, so I know you don't like groups, but it's a nice tradition here, so we thank the speaker. So, you want first?
Need to run and see later.
So I can see how this would work really well with written text. Do you know how to try and apply this, or do you have ideas of how to apply this to spoken language, where pragmatics plays such an important role?
So one of the ideas of compositionality is the fact that actually, I was explaining before how word meanings come together to sentence meaning, but that's not how it works usually. It's also the other way around, like that the bigger meaning actually defines the word meanings. And that's where pragmatics actually comes in. And so the sort of this, I don't know whether I've got a nicer circuit. Okay, here I've got another circuit of these circuits. So it's really that we don't treat words meanings separate anymore or in isolation. We actually train the things in context, within the bigger context of the bigger text. And then the pragmatics is automatically going. So the whole notion of compositionality, as was defined by philosophers, was really that you can understand the whole when you understand the parts and how it is connected. Now, if you think of a quantum state, an entangled state, say a Bell state, this makes no sense anymore. For me, this is a composite system, but it makes no sense anymore because the individuals are just noise. They're just pure noise. So the only thing there is the state itself, the entangled state itself. So the compositionality principle, as was attributed to Frege, it was not him. People before came up with that. But that compositionality principle completely breaks down. It also completely breaks down with language, actually. And that's what machine learning has learned us. What?
That was my question, Lloyd. Before you actually addressed it, my question, when you mentioned compositionality, I was like, wait a minute.
But yeah, so I mean, I wrote a paper about it, like compositionality as we see it. And then, I mean, I don't give many answers, but I'm basically saying like stuff like this. Quantum compositionality, linguistic compositionality is a very different beast than what people have understood it. And that's why, I mean, they were just doing this Montague truth-false stuff in linguistics, and it was perfectly okay for all of that, this idea. But once you go now to the machine learning stuff, that's why all these old formalisms for linguistics are now pretty useless, because they were all built on understanding language bottom up. And here it's all just like one big circuit, quantum circuit, which lets everything communicate. So one argument in favor of this is the pragmatics. Another argument in favor of this is interpretability. You still see what's going on. You see where the words are. I was talking to a big bank 2-3 weeks ago who want to work with us. And everybody is, of course, bragging about ChatGPT-3 and how good it is, except for Italy. Banned it. And this, what? There's a list of 4. I mean, I predicted that, by the way. I predicted that. So I was talking with these banks, and they say, okay, these tools would be fantastic for us, but we're not allowed to use them by the financial regulator because they don't want the second financial crisis generated by something they don't understand. Which is a very, very valid concern. And that's why this is interpretable stuff. There is no counterpart outside of our formalism. There exists nothing else. And this one likely needs to be in a quantum computer. So you see the argument. This one is interpretable.
When I asked about spoken language, there are things you can do in spoken language that's really hard to do in written language. Sarcasm.
Yeah. I mean,
and intonation. If I say look and point, or we're having an argument, I say look.
Yeah. I mean, the way the large language models do this now by actually seeing the same kind of sarcasm appearing 50 times on the internet, so then they can be supposedly sarcastic because they just imitate what they see. To get really to the core of sarcasm, people have been talking, I mean, metaphor is the big one. Analogy, metaphor, those are the 2 real big challenges. And then you're going to need to have some theory of abstraction. It's a technical term, abstraction, abstract interpretation, where you basically throw away certain properties and then see how you can match up and stuff like that. But again, that will need interpretability. You're not going to get away with like a new sentence which a machine never has heard, and then identifying whether it's stochastic or not without something that's more interpretable. So this is now the future of interpretable natural language processing, but it has to be quantum, as far as we think.
Was this sarcasm or?
Are you a machine?
I have more questions. So I want to go back to the quantum stuff. So I'm going to play devil's advocate for a minute because I think that the diagram stuff is beautiful. Of course, I learned the Penrose diagram stuff as a grad student, so I'm biased. But to play devil's advocate for a moment, though, I mean, I suspect one of the reasons why, say, a lot of condensed matter physicists are not going to think very highly of this is because they want to do things like calculate the density of aluminum using quantum mechanics. And I believe you when you say that there are these completeness proofs, but I have to imagine that doing something like calculating the density of aluminum is going to be unbelievably hard.
It's a justified comment for what I showed. What I showed, the completeness is equational completeness. I mean, you can. I'm not talking about like a differential equation. I'm talking about an equation between matrices or compositions of matrices. Anything you can prove in Hilbert space, you can prove there. Now, in recent work, and now I'm talking the last year and a half or so, and that's the same calculus which I mentioned in the context of photonics, which is EXW. We know how to integrate, we know how to differentiate, we know how to exponentiate, we can write down Hamiltonians, and now we're trying to see whether we can get stuff like that out. But it's a new generation. It's well beyond ZX calculus. It's called ZXW calculus. And that's the book I'm writing is like picturing quantum photonics because it's particularly suited to do all. I remember Shazlov asked me like, when was it again, 10 years ago, hey, can you do a beam splitter? With ZX calculus, it's not easy because it's made for circuits and stuff like that. It's not made for photonics. There was another calculus called ZW calculus, and there you got native beam splitters. So W refers to the W state, by the way. It turns out that if you take the G at Z state, it's like times. If you take the W state, it's like plus. So they're very different states in their sort of arithmetic field. And by taking them, so the green and the red spiders, they're all G at Z states. They're all G at Z states, just in a different basis. The W is like a W state. W spiders, I didn't mention them here. And if you smash all three together, you get a superpower from calculus. That's basically it. And that's I mean, the material has been there for more than 12 years, but nobody actually bothered to do it. And then when the kids started to do it, they started to differentiate, they started to integrate, they started to do all that stuff. What it actually does, so yeah, I mean, it's universal. It's universal. You can express anything. Any matrix can be any matrix can be expressed in it. But what it mainly does, from the perspective of a circuit, okay, here I've got some pictures of a circuit. It takes something like a C0 gate, which is a C0 gate here. Here, this is another calculation with C0 gates. It takes something like a C0 gate and it breaks it up in two pieces. And these two pieces are really easy.
So, like, no, my question is actually, like, there's something you cannot represent in the circuit model. Like, one example are like process matrices and like indefinite causal order. And I'm wondering if you can also represent it in this form.
This is not just about circuits. This is just about all of linear algebra, and this can model all of Hilbert space and other theories. So there is no problem doing that sort of process matrix stuff in this language. There's papers about it. In a way, this was sort of going hand in hand to some extent. We've been in grants together for 9 years because of these connections.
Okay, thanks.
I mean, by the way, this should be interesting for Shazlov. I have to show him this picture. The picture was on, but he probably didn't realize it. Okay, here. So you see, clumsily is an higher order process on top of dense. C's is a higher, so you got all this higher order stuff going on in language 2, very naturally. Like an adverb is like a supermap on a verb. So you got all that stuff going on here. So we actually use techniques from people working on process matrices to implement that stuff.
So if you have all the components of quantum circuits, can this be used to help develop new algorithms?
Yeah, I mean, you would expect that, like, and the place we're now doing this is mainly in the space of quantum photonics. I mean, what I'm talking about here, some of the stuff are new quantum algorithms. The thing with linguistics are generally new. It's a completely new space of quantum algorithms that nobody ever considered before, and it's much more like simulation than it is like, say, Shor's algorithm or anything like that. So it's a completely new space of algorithms which we are developing, and I mean, the language which we use always diagrams. I mean, I can't speak in any other language anymore. I kind of lost all the other stuff. So yeah. But I mean, quantum computing is a lot more than just algorithms, and that's sort of what these people from QIP and these conferences never realized. You got compilation, you got optimization, playing with fault tolerance, and those are all the places where the diagrams immediately were adopted. The first places, all this other stuff that you need to do if you want to make practical quantum computing, which the algorithms people never considered.
Yeah, but it would be interesting if you can go backwards.
Yeah, exactly. I agree. I completely agree.
It's pretty hard to develop algorithms for some classical, like partial differential equations.
Yeah, exactly. Yeah, I mean, we haven't looked much into this, but now, like, because of these connections I was just mentioning. With Hamiltonians and differentiation and integration, like some of my people are now working with the quantum chemist, to see whether this stuff can actually help with quantum chemistry algorithms. And the chemists seem to be very optimistic about it. Because we got a big team of chemists in our company. They're based in Cambridge.